Have you ever wondered how your computer lets you watch a YouTube video, download a file, and edit a document all at the same time without crashing? It's not magic. It's all thanks to something called a thread. Think of a computer process as a big project, and threads as the team members working on different parts of it, each doing its job, but all sharing the same tools and workspace. Threads are what make your apps feel fast, responsive, and smart, like multitasking superheroes behind the scenes. Let's dive into what threads are and how they work. What is a thread in OS? A thread is the smallest unit of execution within a process. It's sometimes called a lightweight process. Threads share the same memory, code, data, files of the process, but each has its own register set and stack. Imagine a web browser. One thread loads images, another plays videos, another handles user input. They're all part of one process, the browser, but doing different jobs. Why do we need threads? Threads allow parallelism. Multiple tasks can run concurrently. They reduce context switching overhead compared to processes. Efficient use of multi-core CPUs. What are the types of threads? A. User-level threads, ULT, managed by the user space libraries. OS doesn't know about these threads. Thread switching is fast, but if one thread blocks, the whole process blocks. Example, POSIX threads, pthreads, running on user level only. Analogy, like a group of friends managing their own tasks without informing the teacher, OS. B. Kernel-level threads, KLT, managed directly by the operating system kernel. The OS schedules and manages these threads, can run in true parallel on multi-core CPUs. Example, Windows, Linux threading models. Analogy, like students in class being monitored and directed by a teacher. OS. C. Hybrid threading models. Combine user and kernel threads. User-level threads are mapped to kernel-level threads via models like M to 1, many ULTs to 1 KLT, 1 to 1, 1 ULT to 1 KLT, M to N, many ULTs to many KLTs. Example, Solaris, Windows 7 Plus. Many to 1 model. Multiple user-level threads are mapped to a single kernel-level thread. How it works? Thread management is done in user space. The OS only sees one thread per process. Pros, efficient thread switching. No kernel mode switch. Portable and simple. Cons, if one thread makes a blocking system call, all threads block. No true parallelism on multi-core processors. Analogy, imagine many employees reporting to just one manager. If the manager is unavailable, everyone's work stops. One-to-one model. Each user-level thread is mapped to its own kernel thread. How it works. OS manages each thread. Can use multiple processors for true parallelism. Pros. Allows concurrent execution. A blocked thread doesn't block others. Cons. Higher resource usage. OS has a limit on how many threads can be created. Analogy. One employee reports to one manager. More independence but higher cost. Many-to-many model. Many user-level threads are mapped to many kernel threads. How it works. The OS can schedule kernel threads on multiple processors. The runtime system decides how to map user-level threads to kernel-level threads. Pros. Good scalability and flexibility. Avoids blocking problem of M to 1 and overhead of 1 to 1. Cons. Complex to implement. Needs advanced thread library support. Analogy. A pool of employees is managed by multiple supervisors. Tasks can be balanced dynamically. Problems with multithreading. Multithreading adds powerful concurrency, but also introduces complexity and risks. Let's look at the major issues. Race condition. Occurs when two or more threads access shared data at the same time, and the final result depends on the timing of execution. How to fix. Use locks, mutexes, or semaphores to control access. Deadlock. A situation where two or more threads are waiting on each other to release resources, causing all of them to get stuck. How to fix? Avoid circular wait, acquire locks in a fixed global order. Live lock. Threads keep changing their state in response to each other, but no progress is made. How to fix? Introduce random delays or back-off strategies. Starvation. A thread is perpetually denied access to needed resources because others are constantly prioritized. How to fix? Use aging technique, increase priority over time. Context switching overhead. Switching between threads requires saving and loading state, which can reduce performance if done too frequently. How to fix? Design thread granularity carefully and minimize unnecessary switching. What happens internally in a thread? Each thread has its own program counter, PC, stack for function calls and local variables, registers, shared access to code, data, and files of the parent process. Why are threads called lightweight processes? Because they share resources and have less overhead compared to full processes. What are some common use cases for threads? Real-time systems, multimedia apps, web servers, or any system needing concurrency. That's a wrap. If this video helped you, make sure to hit like. It really helps. And if you think your friends could use a little OS wisdom, go ahead and share it with them. And of course, don't forget to subscribe and hit the bell icon so you don't miss out on future videos. See you in the next one. Until then, happy learning.